The future of life is a pretty bold subject to address, so we thought we might as well start with a very bold question for the first panel. What do life's origins tell us about life's future? To consider this, we've brought together, to join Paul on stage, 4 wonderful panelists. Paola Caselli, who's the founding director of the Max Planck Institute for Extraterrestrial Physics. And then 3 more Nobel laureates from 2019, 2020, and 2021. From 2019, we have Didier Queloz, who Laura had already mentioned. From 2020, we have Andrea Ghez, who received the Physics Prize for proving the existence of the black hole at the center of our universe, of our galaxy. Whoops. And from 2021, we have Benjamin List, who discovered a new method in organic chemistry, organocatalysis, co-discovered with, but independently discovered with David Macmillan. Now, guiding this amazing group in conversation, a daunting and enviable task, is Julien Zeerath from Karolinska Institute, a member of the Nobel Committee for Medicine. Julien, your panel.
Thank you, Adam. So this is going to be a great panel, and I want to start actually by surveying the audience. So, excellent lecture, Paul. Based on that, how many of you are hopeful that we will be able to take what we've learned from the past to inform us about the future? So just a show of hands. It's almost unanimous. Nice. But we're here to discuss that. And so one could perhaps rephrase the question, what have we learned from our studies of the origin of life, and how will that help us navigate the future? And Paola, you're an astrochemist.
I am an astrochemist.
You've thought a lot about this.
Yeah, well, I would really like to understand, in fact, how life originated on Earth. I'm not the only one, I guess. And this is from what I know, from what I'm studying. We know that molecules and actually building blocks of prebiotic molecules are everywhere in our galaxy, and not only in our galaxy. We start to see these big molecules also in high redshift galaxies. So chemistry is, I think, the same everywhere. The conditions are different. And what we see is then when we look closer into our solar system and say primitive materials, so the building blocks of our planets, our Earth, we see actually all the building blocks that Professor Nurse was talking about. So we see amino acids, we see nucleic acids, we see sugars, we see everything, even more than living beings need. And in fact, what I think could be great at some point to prove is that all these original blocks are actually present at the very beginning, and depending on the environment where these building blocks land, it could be the Earth, but it could be other exoplanets, then there will be a chemistry that will actually lead to polymerization and to complexation and finally to living beings. So I guess that I cannot prove this, but from what we see also in other regions where planets are forming right now, it seems that probably life is going to be easy to form, because life on Earth formed soon after the formation of the planet, actually soon after the formation of the moon. That was a very violent event and was 4.2 billion years ago. So I expect life to be widespread, and of course the conditions to complexity will be different depending where, which type of conditions are in a planet, and the future of life will depend then on the more complex beings like us. If we wanted to keep this going well, we really need to take care. And so I really much endorse the last words of Professor Nertz, because this is so important. We are the first one that we understand this. So please, let's keep looking at that and say we are the only one who can save ourselves to have a bright future and, you know, evolve even more. I don't want to take more time.
Do you want to respond to that at all, Paul? Just
not yet.
Okay.
Let's hear what others say. I will at the end.
All right. So, Andrea, your perspective as a physicist.
Oh, I think I'm going to take a slightly different tact on this one.
Yeah.
As somebody,
that's the point, because
yes.
this is very bold and broad.
Oh, indeed. I could not think of a bolder one
Yeah.
to ask. So I think it's interesting to ask, how capable are we of thinking about the future from our what we know today? And I think looking at the history of astrophysics, we're not very good at it in one sense. You know, we started thinking that the Earth was the center of it all. Then we went to the solar system, or the sun being the center of it all. Then the galaxy. I mean, only 100 years ago, we thought the whole universe was just our galaxy. So I think it's really interesting to ask, how good are we at understanding or extrapolating to the larger scale from what we know today?
Dieter, physicist as well, another perspective from that point of view?
Yeah, I think as a physicist, I tend to simplify things. And the question what we know about the origin of life, to me, we know a couple of things, I think, for almost certain. Well, for certain, I would say. First, it happened. Well, I think when you think about that, it's not something obvious. When you think about matter, when you create the universe, you create matter. So you create matter. And then it happened. You create life on the solar system. We know it happened on the solar system. And it's already something absolutely amazing. So this is one fact. Now, the second one is we know, up to now, that there is only one single form of life. That was clearly said with the talk before by Paul. Well, that's interesting already as a fact. We know that there is one single form. Is it the only one? Then you can scale down and you can go to the building blocks and you can argue at what moment you can start diversifying, and then when you can look back at the history about life on Earth. And there is something which is quite fascinating is it seems that the diversity of the basic functions of life has not changed that much. It was very quick, that was mentioned before, and then we're growing, we're developing, you combine cells together and so on and so on. But actually the very, very basic element was there from the very beginning. So there is this kind of a feeling that because it happened once, it should happen many times. Because it happened on this solar system, it should happen also in other solar systems. And since it happened pretty quick, and it seems that I think the beginning was pretty quick to assemble the main functions. I think maybe the main functions are kind of similar, and there is a point that you could expect. Then there is a moment which I think is fascinating, is life has a major impact on the planet. And as an astrophysicist, this is really super exciting because it means we can detect it without detecting life itself. We just try to detect the impact of life. And now you open the Pandora box, are we sure life started on Earth? Very likely, I think, but let's have a look. Let's have a look on Mars. Well, it's good because we're doing it. Then Venus, still a lot of work to do, but you know, Venus is a sister twin of the Earth. There's no much difference. Same mass, same size. It's a very different atmosphere right now because there is no water, essentially. This is the end game for Venus. But if you look back in time, if Venus had water, which is something we don't know, it should have been very similar to the Earth, at least at the beginning. And then something went wrong, and likely the whole CO2 recycling stopped functioning, and then you end up with a greenhouse effect that is possible or fate if you don't fix the problem. We just operate now with the energy on Earth. So I think all these questions are fascinating, but the fact it happened, the fact we can make progress on the knowledge-based element, this is a complete change. Because it's not only about debating it, it's not only about talking about it. We're bringing new facts, new elements, and hopefully we should learn about the origin of life, at least the one on Earth, and possibly how we sit in the grand scheme of the universe. That's my physics perspective, which again is very, very broad-minded, not at the level of detail that Paul, is developing.
How about a chemist perspective, Benjamin?
Yeah, thanks for giving me this opportunity. Actually, the reason I went into chemistry was for posing similar philosophical question. What is the origin of life? Why are we here? And the funny thing is, the physicists in the Max Planck Society always joke about me because I thought the answer is provided by chemistry, right? Chemists know how molecules interact, and so they should understand all that. And of course, the physicists claim they have the answer. I'm not sure if it's really true. In any case, I think this is a fascinating question, but there's only, well, the bad news is, unfortunately, it is probably impossible to figure out how life originated, on Earth at least, because there are no fossils that report on these early cells. We don't have them. They're gone. And there's a physical reason, I think a geophysical reason. The Earth tectonics push the plates into the inner core of the Earth, and then everything sort of becomes atoms and tiny things again. And so nobody really knows about these origins. And the same is also true about, what's life's future. We also cannot know that, right? So that's the bad news on the one hand. On the good news, though, is, of course, I'm a synthetic chemist. For me, synthesis is a beautiful term. I love to create things, and I'm very much with Feynman. I don't know how he put it, like, I cannot understand what I'm not able to make, right? So the challenge, the ultimate challenge of synthesis, of creating things, should be to make a cell, a living cell, right? And I know there are people trying to do this, like a top-down approach where we try to find like the minimal cell. What is the smallest cell with the minimal requirement? And that already is so complex that no chemist on Earth is at the moment, with the current technology, able to make them. But perhaps one day, there are people working on making the ribosome with chemical synthesis, and that's tough. And one beautiful approach that I foresee is, and I try to make these mirror image molecules, which are somehow associated with the origin of life. How did we have this selectivity that there's only left-handed amino acids and right-handed sugars? And I would find it fascinating to create a live cell that is mirror image. How would that interact with the other cells? So, boom. Yeah. Yeah, annihilation. Who knows?
Well, Paul, the medicine field is really fascinated with this idea of, building cells for the future. So thoughts from your perspective? You gave us a great lesson on that today.
Well, I think we've heard some interesting things here. The first is that life exists. I think, obvious but very important. The second is, and Drake, who recently died, argued that the universe is so vast that the probability of it being elsewhere is not zero. Let's put it that way, because if it existed once, then it's likely to have existed somewhere else. I think that's rather significant for us, but we should accept that. I also think that we could sort of understand how the building blocks, the chemical building blocks appear. So I'm sort of okay with that, and we've heard that. But then we have to put together an entity based on information, an entity that integrates chemistry through information and leads to its reproduction. These are all big asks, and frankly, I feel underweight trying to think about it. I think those, and I'm not somebody who does research in this area, those who do think about it tend to think of maybe there's surrogates, that in fact what we see today isn't actually what started, but provided some solutions to these problems, that you need an entity that needs to reproduce or at least migrate to get some sort of selection. I could imagine things, but it is entirely imaginations, because how do we imagine the chemistry and life of 3.5 billion years ago? It's extremely difficult. I could imagine little cavities somewhere deep in the ocean driven by geothermal energy. I could sort of imagine that some chemicals are being formed there, and that different sorts of chemicals find it easier to migrate elsewhere, maybe. So there's a sort of primitive natural selection going on, that they inhabit more and more of the cavities. And out of that, we get lipids that might make a cell. And then, of course, there's RNA and the RNA world, which we haven't mentioned yet, because the problem that I wrestle with, which is how you combine information together with the chemistry. RNA can encode, but it also can carry out primitive chemistry. So that's been a favorite solution offered by the molecular biologists. how it all goes together, I agree with you. I mean, we can't, it's almost impossible to imagine. The only thing we can say is it did happen. It did happen. And eventually, it led to something, and the most earliest fossils are about 3.5 billion years ago. But there's another mystery, a little bit later. We had unicellular life 3.5 billion years ago. Multicellular life, like us, I mean, not exactly like us, but sort of, you know, wormy sorts of things, evolved maybe 600, 700 million years ago, maybe a bit before that. 3 billion years to go from one cell to a few cells, 500 million years to go from a few cells to us. I don't understand that, and there's something going on there that I think we do need to understand.
I mean, the whole scale of time is just overwhelming because this is really massive. You want to step in, Paola?
No, I just, yes, after hearing this, I think one very important thing from my point of view to do when we want to understand these origins of life is not just look at the chemistry, but also the condition of the early Earth. So we really have to focus on the fact that the early Earth was very special conditions. We have our moon like here. You know, it was very close because it just formed. The rotation of the Earth was very fast. We had day-night cycles, like a few hours, and tides. So temperature must have been different. UV photons, because we didn't have the, you know, ozone layer yet. So I always try, this is what I'm trying to do with my biophysicist colleagues in Munich. Please try to get closer to the early Earth. Maybe that is where the secret is, but who knows?
Benjamin, you look like you're agreeing, or?
Yeah, I think this is a fascinating question. Like, what were the conditions? I don't know. You know, I think
Yes,
the physicist, the astrophysicist, should tell us, and then we can think about the chemistry that would be possible under these conditions, right?
Dieter's chuckling over there. You just tossed the ball to the physicists.
No, look, I love that because I have had so much similar discussions. I'd like to reflect on a couple of points that was said, which are very, very important points. I think there is this fascination element that Paul is sharing with us, and he's perfectly right. I think life looks too perfect right now. When I say too perfect, it's too perfect to be true. When you see all this connection, the communication, and all it works, it's a fully optimized system. And it's pretty clear that it cannot happen like that from the day one. And that's a tremendous challenge to find out what all the elements are building up and lead to that. So as a physicist, again, I love to simplify again. And I want to give you another example. Think about our society. It's amazingly complicated. A lot of rules and communication channel, and there's a lot of stuff going on in society. How much time did we need to reach that level? Think about the origin of our species, how we were at that time. So you understand that the growth of complexity is not something magical. It can naturally come into a system. Of course, you need a sub-series element to make it happen, but you can grow to something very simple, which is just tribes somewhere here with the minimum organizations, to a global tribe, which is 8 billion people on Earth, which is sending people to the moon and to Mars soon. So it's not a problem for me, the growth of complexity for life. I think it can come for free. The problem is, how do you assemble the right ingredient maybe at the right time, and maybe the origin of life, the condition on Earth was critical. Maybe the moon was essential. So if you need exactly the same kind of planet and exactly the same kind of moon, then the chance to happen elsewhere would be much more smaller, because this event was very rare in a sense and as an end product, because it could have completely blown out the Earth. It didn't, but it blew out the Earth enough to create the moon. So I think this element of life is always a bit challenging, because we have now a kind of a very, let's say, high-tech flying machine. And we're trying to understand the early experiment when people were trying barely to fly with simple machine. And this is really the big step we have to do. It looks complicated because the jump is immense, but practically as soon as you start assembling it and think about the development of knowledge in our society, think about the acceleration of the knowledge in our societies. The fact life has accelerated from very slow to higher and higher and faster. It's not a surprise, because you see that in many organization systems. So again, I don't try to understand the building blocks, and you're right, when you look at the detail, it's just mind-blowing. I agree with that. But on a global scale, it's fine for a physicist.
All right, Andrea, your thoughts?
Oh, I always come back to the Drake equation that, the universe is immense, and I think there's lots. It's a big experiment, one that went very well here, and I think it'll be interesting to see where else we find life.
And you alluded to that it might be much like us, or perhaps not.
Finding life, you mean? Yeah.
Yeah.
Well, if we did find life, it would help us understand our own life. So that for me, intellectually, is the most interesting thing. What it means metaphysically, philosophically, is another thing. What it means to our emotional condition. But if we see life elsewhere, let's say Mars or one of the moons of Saturn or wherever, if it is, will it be built on the same principles, the same chemistry? That would tell us something. Will it be built on something different, which might tell us more? Going beyond our own solar system, we just have to rely, I think, on, surrounded by physicists and chemists, on the chemical signatures around the atmospheres of planets. And whether that will give us, it might tell us there's something there, but what is there, I'm not so sure it'll be so informative about. But it would still be a wonderful thing to discover it, I think.
Right.
So, I think we first of all have to be a bit humble about this. This is a great mystery. We should not pretend it is easy. Once we have a primitive life form, I can see it could work. Complexity will come. It may take 1 billion years, but it could happen. How it's come together with these parallel strands, I struggle with. And I think we have to have a bit of humility as scientists in thinking about it.
So much of what we do is based on fundamental principles, and to some extent we think then it's a bit predictable, but I'm hearing a lot of this is unpredictable. Any thoughts on that? I mean, how much control do you think we have?
You mean, should we be reading the science fiction authors? Maybe we should. Maybe we should.
Dieter, go ahead.
I made a joke during my Nobel lecture about this at the end. And I said, well, I mean, life is a bit like when you have a chemical experiment that took over the experiment. And this very moment is very, very special. We don't understand that in a way, because it's chemistry. Usually you do have to do something for chemistry. But there's a moment when the experiment is kind of functioning enough. It doesn't need anybody to do it. The experiment itself starts to take control of it. And this is something we have not been able to do. That's tremendously difficult. That's understood that. But that's exactly the challenge here. And then the more you evolve, the more you decouple from the outside elements. So the way we are amazingly isolated from the outside need. We have just basic need, but we don't need extravagant chemistry. We grab very simple stuff, and then we make it magic because all this amazing factory we have into the body. But at the very origin, it may not have been like that. Actually, we were in a need of a lot of chemical around us that was needed to maintain alive. And then the more they develop, the more they get rid of this, because they get rid because they managed to make it at some point. So this is this kind of battle here. How far do you decouple from the inert material you have around that you're using it for you to stay alive that nobody understands? And maybe it's going to take 100 years to find this out. But with the progress of the chemistry right now, the analytic chemistry and the machinery people is doing, I'm very much optimistic. Think about 10 years ago. The big challenge was to make the human genome. Right now, it's just 10 minutes into a computer. You send your stuff and it comes back, and that's it. So I think, the knowledge, the growth of the knowledge, our society, the global society we're operating right now, is such amazing as a global entity of building the knowledge. So I'm pretty sure that even if the problem is tremendously complex, I would agree, it happened. So one day or another, we're going to understand it.
So I think that's a great place to end. I think there's so much more to learn that we should continue to be in the pursuit of new knowledge, and that will definitely help us understand a bit more about the future, even though we don't have crystal balls and can't predict it all. So thank you, panel. Thank you very much.
Thank you. Thank you.
Okay. We're just going to go this way.